recording. Okay, so yesterday we discussed about binomial distribution. Okay, we defined what binomial distribution is. Remember that. We also discussed about three major assumptions. Okay, three major assumptions of binomial distribution. Okay, where we say the first assumption is that there is only two possible outcomes, okay, in each trial. Okay, so you only have two possible outcomes. Remember, we say that it might be a win or that is a lose. We have yes or no. Okay, we have success or failure. Okay, remember that. So these are just that is examples of that is two possible outcomes. Okay, like and I remember giving you an example of that is tossing a coin. Okay, it's either we get what, a head, or that is a head or a tail. Okay, a head or a tail. Those are that is one of the example of a trial which can give us two possible outcomes. Okay, the second assumption was that is each trial has the same probability of success. Okay, each trial has the same probability of what? Same probability of success. Okay, good. Then we also say that each trial is mutually exclusive. Okay, each trial is mutually exclusive or independent to what? To each other. Okay, like the outcome of one that is of the one trial does not influence or affect the outcome of the what? Outcome of the second trial. Okay, we also discussed about some of the examples, common examples of the binomial distribution. We also discussed about that is the properties of binomial distribution, and we say that these properties are more of the same as the what? As the assumptions. Okay, they are more of the same. Okay, we also saw that binomial distribution is what? It's a discrete distribution. Okay, it is a discrete distribution, and we also summarized it. Okay, and we gave an example. Okay, like maybe when when in a election. Okay, it's either maybe a Republican or Democrat will win. Okay, all right. Then we also discussed about the formula. Okay, the formula for binomial distribution. Remember that we also that is discussed about the formula, and also we did an example. Okay, we just assumed an example and we did it. Okay, all right, good. Now we also discussed about Bernoulli principle, or sorry, not principle, Bernoulli trial or distribution, and we saw that it's like a special case of binomial distribution, but when the number of trials is equals to 1, or when n is what? Is 1. Okay, all right. We also did some takeaways, and then today I want us to introduce that is a new distribution, which is the last distribution. Okay, it's our last distribution. Then I will give you one distribution to research, which is a very easy distribution. So you can go and research about what? The exponential distribution. Okay, please go and research about exponential distribution. Okay, you can that is research on what is what is the what what is exponential distribution. Properties of we have properties of binomial of exponential distribution, that you can also that is research on some of what examples of binomial distribution, sorry, of exponential distribution. Then fourth, you can also check maybe some practical applications. Okay, practical applications of what, of binomial of exponential distribution. Sorry, I don't know why I keep confusing exponential and binomial when pronouncing that, or maybe it's because they are all ending with no. Okay, yes, so go and research about exponential distribution. Okay, and please research it without fail. Okay, because maybe you might find it is the one which is being tested. Okay, yes, but remember that you will be tested or that is the curriculum only covers that is these five major what distributions. Okay, normal distribution, binomial distribution, Bernoulli distribution, Poisson distribution, and exponential distribution. Okay, you can go and check on it. Okay, so in case maybe you miss that is more information about exponential distribution, please just reach out to me, and then maybe I will share some few slides with what, with that is those details. Okay, these four details. Okay, and exponential distribution, right? Good. So I'm missing exponential distribution in these slides, since in fact in all previous statistics classes I gave it as an assignment. That's why you can see it in my slides, but I can always support in case maybe you find those properties and you can get them, or in case you want some the definition. Okay, all right, now let's come to our Poisson distribution. It's also known as count distribution. Okay, count distribution. It's also known as count distribution. So let's start and see what this distribution as. Okay, for us, so we'll do some that is definition, because we have an extended definition here. We also have the formula for exponential distribution of Poisson distribution, sorry. And then we'll also discuss about some of frequent questions and distributions. Then we'll do some that is some takeaways, and then that is try to understand. Okay, that is understand Poisson distribution. Okay, or we'll try to do a mathematical example of Poisson distribution. Good. Now, in statistics, Poisson distribution, by the way, before I can continue, we are all together up to that point? All good up to that point? Nice. Correct. Thank you. Okay, so Poisson distribution. What is Poisson distribution? So Poisson distribution, it's a probability distribution that is used to show how many times an event is likely to occur over what? Over a period or over a specified time period. Okay, it's like you remember in that is in physics when we were doing that is oscillation practical. Okay, we are trying to see how many complete oscillations will we get, maybe within what, 3 minutes or within 1 minute. Okay, how many number of oscillations, okay, will we get within 1 minute or 3 minutes? Okay, so it is kind of applying the same knowledge here. Okay, like remember, this is what we are checking: how many times an event is likely to occur over a specified period of time. Take note of that. So we are checking how many times an event will occur. But when we are now discussing about the probabilities, we will be doing like probabilities of maybe an event occurring a certain number of time, that is times within what, a specified period. Like for example, let's assume um every Friday you are working with on that is cheese, okay, or burger outlet, okay, or a pizza in outlet, okay, and we know that on a day like Friday, we usually or we averagely sell 200 pizzas. Okay, we usually sell or on a normal day, we usually sell 200 pizzas. Okay, on a Friday night. On a Friday night, it is giving us now the aspect of what, of time. Maybe night might mean maybe within 3 hours or within 6 hours. Okay, night hours. Okay, so the night is giving us the aspect of time. Okay, then we have the number of pizzas sold. Now they are like the what, the number of events. Okay, so we might decide now to do a probability that next Friday we will sell more than 200 pizzas, or we will sell more than 280 pizzas. Okay, so that will give us the probability that for sure we will what, will that is, will sell maybe 80 more pizzas compared to the what, to the normal Fridays. Okay, yes, but don't worry, I will illustrate that as we move on. Okay, good. In other words, it is account distribution. Okay, it is account distribution. Poisson distributions are often used to understand is used to understand independent events that occur at a constant rate within what, within a given interval. Okay, so it was named after a French mathematician, okay, Simeon Denis Poisson. So this is that is the author of what, or the publisher of the first publisher of Poisson distribution. Okay, yes. So it's Poisson. It's the one who came with the what, who came with the concept of Poisson distribution. So the Poisson distribution, of course, if it is a count distribution, makes it to be what? To be a discrete distribution. Okay? Meaning that the variable can only take specific values in a potentially infinite list. Put differently, the variable cannot take all continuous values in okay, it cannot take all values in any continuous range. Okay, so for Poisson distribution, the variable can only take whole number, whole number values, either a 0, 1, 2, 3. No fractions, no decimals. Of course, that's what differentiates what? That's what differentiates, that is fractions, that is from the that is not fractions, but that's what differentiates discrete from what? From decimals. Good. Let's continue. So, in statistics, Poisson is one of the important topics. It is used for calculating possibilities for an event with average rate of value, okay, to occur. For Poisson, that is Poisson distribution, of course, as we had said, it's a what? Discrete probability distribution. So the Poisson distribution, of course, it's like more of a repetition, means that the variable can only take specific values in a given list of numbers, probably infinite. So a Poisson distribution measures how many an event is likely to occur within X period of time. In other words, we can define it as the probability distribution that results from a Poisson experiment. A Poisson experiment is a statistical experiment that classifies the experiments into two categorical, that is such as success or failure. So for Poisson distribution is a limiting process of what? Binomial distribution. Okay, it is a limiting it is a limiting process for binomial distribution. Okay, so a Poisson random variable x defines the number of successes in the what? In the experiment. This distribution occurs when there are events that do not occur as the outcomes of a definite number of outcomes. Okay, so Poisson distribution is used under certain conditions, like for example, where a number of trials n tends to what? To infinite. Okay, where the probability of success, that is P, tends to 0, and where that is the number of trials multiplied by the probability of success, you will get what? You will get a 1. These are just conditions, okay? Conditions for Poisson distribution to what? To take place, okay? That is the number of n tends to be what? To be infinite. What does infinite mean? Okay, what does infinite mean? Like the difference between infinite and what? Finite. Okay, yes,
To
yes,
me,
Belinda.
infinite means something which is never ending, that is like continuous, it's never ending.
It's
Like there are very
endless.
many possibilities.
It is endless. That is in size. Okay, yeah, like it has no, it's perpetual. Let's say it's perpetual. Okay, yes, and then finite is something maybe which you can do what? Which you can, of course, count, right? Yes, like yes, that is some limited, that is size, or it is limited in terms of size. Okay, all right. Then before we can come, we have there is somewhere I had the formula. Okay, yes. Let's come maybe to the formula of Poisson distribution. So let's say we usually say that a variable is Poisson distributed, or that is the probability. This is the function and also the probability. Okay, so it means that that is for any Poisson distribution, okay, it has a function, or the function of x is equal to, okay, exponent raised to negative what? Lambda. And you will find that this lambda is the x bar, okay, or this lambda, it's what? It's the expectation of Poisson, or it's the mean of Poisson. Okay, so we have exponent raised to negative what? To negative lambda. Lambda here, it's equal to mean. Okay, multiply by lambda, okay, raised to what? To x. Lambda raised to x. Okay, we shall also discuss what is x. But x, let's say, let's assume it's the number the number of I don't want to call it trials, but they are number of events. Yes, the correct term is x, it's equal to the number of events. Okay, then all this divide by what? X factorial. In fact, let me remove this raise. So basically, function of x, following, assuming x is following Poisson distribution, is given by exponent of negative lambda multiplied by lambda raised to x, okay, divide by what? X factorial. Okay, then we've said that the mean of that is of the Poisson distribution, it's what? Is lambda. And Poisson distribution is the only distribution where mean is equals to variance. That is, mean and the variance is the same. Okay, so variance of lambda, it's what? Sorry, the variance of the Poisson distribution is equal to mean. Okay, let me maybe confirm that. Let's confirm that. Poisson distribution. I need the Wikipedia one. Okay, you can check this. Okay, so you can see the mean of Poisson distribution. Okay, it's the same as what? Its variance. You can see mean is lambda, variance is lambda. Okay, yes, so this one is the one that is, it's the only distribution where mean is equal to what? To variance. Then it has its median, it has its mode, it has its skewness, it has its that is kurtosis. Okay, and then probability mass function, you can see it's what we have explained. That is exponent of negative lambda, okay, multiply by lambda raised to k, whereby k, it's the number of the what? It's the number of events. Okay, divide by what? Divide by k factorial. Okay, you can come here and maybe research more on this. Okay, like for example, I can see we have some examples here. So like under Poisson, we can see that the Poisson distribution may be used to model events such as number of students achieving a low and high mark in an exam, number of lesser that is photons hitting a detector in a particular time interval, and number of that is meteorites, okay, greater than 1 meter diameter that strike planet Earth in what? In a year. Then we also have some assumptions, okay? Some assumptions. All these, they are what? They are conditions, okay? They are the conditions which we've discussed. Like, for example, the K is the number of times, or it's the number of times an event occurs, okay, in an interval or in a given period of time, okay. And also the occurrence of one event does not affect the probability that a second event will what? Will occur. Very correct. This is another point which I don't have in the that is in our notes, okay. But you can always add that point, okay. You can always add that point. Like, also here, the events are what? They are mutually exclusive, or they are independent of each other, okay. Yes, that is, the occurrence of one event does not affect the probability that the second event will occur. Another one is the average rate at which event occur. It's independent of any occurrence. Okay, for simplicity, this is usually assumed to be constant. That is the average rate. Okay, it's always assumed to be a constant. But in practical, or in practice, this might what? It might vary. Then two events cannot occur simultaneously. Like, the two events cannot occur at what? The same instant. Okay. So this is another property. Okay. So you can go and take these points, but let me try and see if I can add them for you, that is to make it simple for you. Okay, where can I add it? These are some of assumptions. They are some of assumptions which may be that is you can use, or properties. Okay, in Poisson distribution. Okay, you can check out this. At least us going to check to confirm that is the mean and the variance. It has also given us somewhat that is some properties, okay. Yes, of Poisson distribution, okay. Yes, then I guess the others are just examples how maybe you can calculate all those properties of binomial distribution, okay. Yes, so under properties, okay. Right, we can now continue. So we've already gone through those assumptions. You can later check on them, okay. Any question maybe up to that point? Any maybe question up to that point? Are we together up to that point? Yes. Kinder?
Good evening, everyone. My question I would like to ask, based on the yesterday's class and today's class on distributions, as a statistical student, or maybe statistical profession, do we first of all, I like the scenarios in which you can be given a statistics to make sure to calculate the distributions if you are given a data set in that manner. Number two, I would like also to ask, are you expected as a statistical profession to master or memorize these formulas for you to generate the distribution, or there is also maybe an inbuilt Excel tool that you can use to get those ones. That was my concern.
So let me start with the first or with the second. So for the second, yes, we have inbuilt formulas in Excel, which will help you to do what? To do that is to do that like to fasten your process. Okay. About that is the formulas. It's good you have them, not really in your mind. Okay, but the formulas, like you can explain the formula. Okay, you know what when we say exponent, that is lambda. What are we in Poisson? What is the lambda? What does the lambda represent? Okay, when we are talking about maybe x or k, what do you know? That is, what do you know what x or k stands for? Okay, that's what you need to understand in those formulas. Like you understand the general what? The general idea behind that formula. Okay, but not to memorize the formula. The formula, no need to memorize. You can always access it, that is on websites. Okay, it is everywhere, so you can always access it in what? In that is in your websites. Okay, or online. Okay, then the for the that is for the first question, that is like some practical examples. Okay, so tomorrow, that's what will be, and from that is starting from tomorrow, that's what will be handling, because remember, now tomorrow we'll be doing the practicals of the what, all the some of the application. Okay, of this distribution, but practically, whereby we shall be calculating those probabilities. Okay, like for example, we'll do now using Excel. We'll calculate maybe probability of 1, 2, 3 or 4 events occurring. Okay, we'll just take a scenario. Okay, even if it's that is a very basic scenario. Then about now the applicability in your workspace, you can now try to check how can your data, maybe your available data, being used to what, or how can we know this data follows a normal or a binomial distribution. Okay, so for you for you to easily identify, okay, the kind of distribution can fit your data, you must have the properties of the properties and assumptions of those distributions at your fingertips. Okay, yes, like for example, if we are talking about that is we that is the occurrence of each event, it's what, or of each trial or experiment, it's independent. Okay, meaning it does not influence the outcome of what, of the second trial or experiment. So with that, you will be knowing that here maybe I'm either dealing with binomial distribution or Poisson distribution. Okay, only those two. Okay, if maybe you narrow it to binomial, okay, then you find that we are only given the chance to do what, to perform one trial. Okay, if now we are performing only one trial, then it will no longer be what, binomial, rather it will be what, binary distribution. Okay, or binary trial. So with that, the properties will always help you to know which kind of distribution your data that is your data set will follow, depending with those properties. Okay, about applicability of the distributions in your maybe on your work, that is data, we'll try to do an example tomorrow. We'll try to mirror a real life that is a real life example. Okay, So please remind me that is tomorrow. So if maybe you have your data, you can always, and it's not confidential, you can always, we can always have it to practice with it. But I usually don't, that is encourage that, because it is a breach. Maybe it can be, it can lead to a breach of maybe personal data, okay, or maybe company's data, okay. Or you might find maybe someone is giving, it's using that opportunity to complete his research work, okay. But it's good to go and maybe practice with a real data, or with that is a real application out there, okay. But I can always guide, okay. But I don't like interacting with the other companies data. It might, we have that policy, okay. We have that policy for data protection. That's okay, Kennedy.
Yes, yes, that's well explained.
Okay.
Thank you, thank you.
All right, good. Let's go to frequently asked questions on Poisson. Before we can continue, let me not assume we are all good. Just want to see thumbs up if we are together up to that point. 1, 2, 3, 4, 5, 6. Only 6. I've only seen six responses out of that is a count of 15 people. But anyway, I hope the others are following. Okay, even if you are not reacting, I hope you are following. Why? Because you are not reacting and you are not asking questions. Okay, all right, good. Let's continue. We have frequently asked questions in Poisson distribution. Okay, so under Poisson distribution, or what is Poisson distribution? So Poisson distribution is defined as a discrete frequency distribution that gives probability of a number of independent events that occur within a fixed period of time. So here we have number of events. They are occurring independently. And here we have the aspect of what? Fixed time period. We have the aspect of what? Fixed time period. So we can say it is like, or it gives us the probability of of a number of events occurring independently within what? Within a specified period of time. Okay. Yes. We do. When do we use Poisson distribution? For any that is data, or any data whereby we have that is a number of events occurring independently, and that is at a constant rate within a given what? Within a given period of time. So we use it when we have some independent events occurring within a given period of time. Okay, so where we have an aspect of events occurring within that is a specific time period. Okay, what is the difference between Poisson and normal? Definitely, this one is first of all discrete. This one is what? This is continuous. Okay, so the major difference between Poisson distribution and normal distribution is that Poisson distribution is discrete, whereas the normal distribution, it's what? Continuous. If the mean of Poisson distribution becomes larger, then the Poisson distribution is similar to what? To a normal distribution. Okay, like when maybe the mean of the distribution is becoming large, but we will have to investigate this, which is very correct. By the I remember in our last class we did this trial. Okay, so we shall that is during the that is our practicals. We shall change, will decrease, and also increase the what? The mean of Poisson distribution, and we'll try to see what kind of distribution are we getting. Okay, when now we are getting, if we will be getting, we will be starting getting that is long tails, then it means as we increase the mean of Poisson distribution, then the distribution, all the data now starts to be what? To be normally distributed. So also remember this, remind this tomorrow. To vary, that is the Poisson distribution mean. Okay, and see what will happen in terms of what? In terms of distribution. Okay, are mean and variance of Poisson distribution the same? Remember, yes, we said that is Poisson is the only distribution where variance and mean are equal. Okay, so the mean and the variance of Poisson distribution are the same, which is equal to the average number of successes that occur in a given what? In a given time period. Okay, all right. Mention the three important constraints of what? Of Poisson distribution. So these are the what? The major, that is, these are the major what? The major assumptions of what? Of Poisson distribution. And we know that, sorry, we have that is the number of trials tend to be what? To be infinite. The probability of success tends to go, that is to be 0. Then the probability of success multiplied by the number of the number of events then equals to what? Equals to 1. Okay, so these are the what? These are the major three conditions for Poisson distribution. Okay, good. Let's maybe check that is or understand a Poisson distribution. Okay, let's take a check that is or understand this kind of Poisson distribution. Okay, nice. So a Poisson distribution can be used to estimate how likely it is that something will happen X numbers of time. For example, if the average number of people who buy burgers from a fast food chain on Friday night at a single restaurant is what? Is 200. Okay. Poisson distribution can answer questions such as what is the probability that we will sell more than 300 what? 300 or the probability that more than 300 people will buy what? Burgers. So the application of Poisson distribution thereby enables managers to introduce optimal scheduling system, like optimal, or you can it can help you maybe do what? Increase that is the capacity of your production. Okay, like you can employ more cooks. Okay, who will help you to that is to cook more what? More burgers. That is if the probability of getting these people, it's what? It's high. If it is low, then there will be no need to do what? To that is to improve or optimize your capacity. Okay. Yes, one of the most famous historical and practical uses of Poisson distribution was estimating the annual number of that is Prussian cavalry that is soldiers killed due to horse kicks. Yes, this is always a funny example or a funny application of Poisson distribution, which of course it's a real life that is application. It is something which is being done. Like for example, let's say you have 300 soldiers, okay? 300 soldiers using what? Using horses, okay? So, what is the probability that within a year we will have 10 soldiers killed due to what? Due to horse kicks. Okay, like soldiers who will be kicked by the horses and what? And die. Okay, yes, so that's another example or application of Poisson distribution. So modern example of estimating that is um, or of estimating the number of car crashes in what? In a city in a given size, like for example, or in a given time. Let's say like in Kenya, we can try and model, okay, or estimate, okay, that is the number of car accidents, okay, that happen that is within what? Within, let's say, within 1 year. Okay, within 1 year. Okay, so we also have another example in psychology. That is, this distribution is often used to calculate the probabilistic frequencies of different types of neurotransmitter secretion. Or if you have a video store and we know that we have average 400 customers every Friday night, what would have the probability that maybe next Friday we'll get what? We'll get 600 customers. Okay, maybe let's try and see that is more applications. Okay, more applications of Poisson distribution. Okay, like real life application of Poisson distribution. Here we go. So let's start with the first one, like example of Poisson distribution, like the number of network failures per week, maybe at your workplace. Okay, if maybe you've been you usually of course experience downtime in terms of network. Okay, you can try also to model, or if this week we received average of 2 that is network failures or system downtime, or we've been averagely receiving 1 or 2 weekly system downtime. What is the probability, or what is the probability that next week we'll have 3 or that is then we'll have 3 like downtimes? Okay, like we have 3 number of what? Network failures, or system failures. Okay, that's how we do what we can use also to that is we can use Poisson. Number of bankruptcies filed per what? Per month. Number of website visitors per hour. Okay. Number of arrivals at a restaurant. I guess this is one that is examples I've been using. And also number of calls per hour at a call center. Okay. Like, for example, the concept of Poisson distribution is highly used by the call centers to compute the number of employees required, to be hired for a particular, maybe volumes of what? Volume in terms of what? In terms of maybe calls. Okay. Yes, like you need to meet a certain service level. Okay, so definitely you will use what? Poisson distribution to know the number of that is employees that is you will use to handle a specific number of calls. Okay, or contacts. So for instance, if the number of calls attended per hour at a call center is known to be 10, then Poisson formula can be used to calculate the probability of the organization receiving 0 calls, 1 call, 2 calls, 3 calls, and any greater that is integer, okay, number of what? Calls per hour, thereby allowing the managers to have a clear idea of the number of calls required to be catered at a different hours of the day. And this definitely will help you to form a proper schedule to be followed by employees. Okay. Also, we can also use a number of books sold per week. Okay, and also average number of storms in a city. Okay, and the number of emergency calls received by what? By an hospital. Okay, all right. So these are just few examples. You can even go and that is research more. Okay, you can go and research more. Okay, on what? On Poisson distribution. Okay, you can also see that analysts that is using Poisson distribution in statistical analysis. So you can see we have analysts frequently use this probability distribution for quality control, survival analysis, and that is insurance analysis. Okay. Yes, like that is you can try to model the number of claims. Okay, maybe which you expect to get within what? Within a year. You might be able now to do what? To model all those number of that is claims. Okay, in your insurance company. Okay. Yes, and many more. Many, many more. Or maybe you can also, when we are dealing with that is when we are talking about survival analysis, you can also try to calculate that is the probability that, okay, maybe we'll have in an maybe in an accident will have maybe a certain number of what? Survivors. Okay, or maybe a specific number of what? Of deaths. Okay. Yes, those are just few examples. You can always that is check on more examples. Okay. Okay, good. Any other example? We have real 5 real life. This we've been discussing this. In fact, let me use this to do, maybe to illustrate, that is an example. Okay, let me use this to illustrate an example. Good, let's take this. Okay, good. Let's assume call centers use Poisson distribution to model the number of expected calls per hour that they will receive, so they know how many call centers representatives to keep on staff. Okay, let's assume, suppose suppose a given call center receives 10 hours, that is 10 calls per hour. Okay, use Poisson distribution calculator to find the probability that the call center receives what? Receives 0, 1, 2, and 3 calls. Okay, good. So here at least we have the average. You can see we have been told that the call center averagely receives what? Call center averagely receives 10 calls per what? Per hour. Okay, I want that one maybe to illustrate. Remember that this is the formula we said for Poisson distribution. That is exponent of lambda, okay, multiplied by lambda raised to x, divide by what? X factorial. Okay, so x is the number of what? The number of trials. So in this case, it will be the number of calls. Either 0 calls, receiving 0 calls in an hour, or maybe we are receiving 1 call in an hour. That is 2 calls in an hour, and what? 3 calls in an hour. Okay. And our assumption is that in that call center, we averagely receive 10 calls per what? Per hour. We usually receive 10 calls per hour. So our lambda here will be what? 10. Our lambda here will be 10. So basically, we want to calculate the probability that we will receive 0 calls within what? Within 1 hour. So it will be equal to, that is exponent of negative 10. Remember, we have 10 as our an average. Then multiply by 10 raised to our number of what? Calls. That is 0. We are working with what? 0. When x is equals to what? To 0. So we can say this is the probability when x is equals to what? 0. So it will be this one. Okay, will be this one. So lambda, that is 10 raised to what? To 0. Divide by what? 0 factorial. 0 factorial is always 1. Okay, 0 factorial, it's 1. So with this, it will be, that is exponent of negative 10. Okay, multiply by any number raised to 0, it's 1. Sindio, right? That's correct. From that is the basic statistics knowledge, right? That's true. I want you to confirm that for me. Any number raised to 0, it is 1. It's that true?
Yes, it is true.
Yes, correct. Nice. Good. So we, and 0 factorial, okay, it's what? It's always 1. So here basically we know that the probability that will receive 0 calls in an hour, it will be e raised to negative 10. That is exponent of negative 10. Let's maybe go to Excel and see because I don't have a calculator which can that is calculate that exponent of -10, then I'll use that is Excel function to calculate that. So right, so it will be equal to exponent. We have this exponent of -10, and we'll get what? Okay. Don't know how I can say this. So this will be 0.00, almost 4 zeros. It will be almost 4 zeros. Okay. It will be almost 4 zeros. You can see it's this one. You can see here. Here we'll have just to round off. Okay. That is this is like saying equal to 0.000045. Okay, so meaning when we round off, let's maybe equal to round down this. If we round this down to maybe we want also to be to 5 decimal places. Okay, it will be what? Okay, this is, sorry, this is rounding down. Do we round off? Let's say, let's use a round. Okay, then we need 5. Yes, we are rounding off. Rounding off, we will use round. Okay, rounding down, it's like we are truncating. Okay, we are truncating down. Okay, yes, so or trimming. So for this, you can see when we round this down, we'll get this value. Okay, and once we get this value, definitely you can see it's the same value here. Okay, let's maybe jump the probability if we will get one call in 1 hour to the probability that we'll get 3 calls in an hour. Okay, and see what will be our computation. Okay, good. Let me illustrate that. So we need that is probability that will receive 3 calls within an hour. So let's now do that. It will be equal that is e raised to -10. Remember that it is e raised to -10. Why? Because lambda, we know it's what? It's 10. Okay. Then multiply by 10 raised to, which is lambda raised to x. So it will be 10 raised to what? Our x. Our x is 3. It will be that is 10 raised to 3 divide by x factorial. So it will be 3 factorial. Okay, so basically this will be, of course, we've seen this. We have seen this one. Okay, and we know that this is 0.000005. Okay, we know that this is 0 point, I guess they are 4 zeros. Yes, they are 4 zeros. Okay, multiply by 10 multiplied by 10, that is 10 cubed. It is 10 multiplied by 10 multiplied by 10. Okay, divide by 3 multiplied by 2 multiplied by 1. Okay, remember yesterday we discussed that is about factorial. Okay, nice. So with this, it will be now we'll cancel the zeros. Okay, so this will cancel with this will cancel with this, and this will cancel with this. Okay, so we'll have 0.05. Okay, divide by this will be what? This will be 6. Okay, So let's do that. So we need equal to 0.05 divide by what? Divide by 6. So with that, we'll get this value. We are getting 0.008333. Let's try and see if it's what we are getting. Here we are getting 0.0757. Maybe let's try and see with Excel if we now decide to do what? To compute it in Excel. Maybe here we might have that is missed, okay, something. That's why we are having different decimal numbers. Okay, so let's try and see maybe where we can that is our values are varying. So this will be equal to exponent. Let's first of all compute exponent of -10. Okay, then we have lambda raised to x, so it will be 10 raised to power 3. We have that form value here, and then we have that is equal to factorial. So fact meaning it's factorial of 3, that is factorial. You can see it is 6. Okay, so with that we are going to say it is equal to this multiplied by this. Okay, then divide by what? We can just put that the formula that is in one cell. It will be now this multiplied by this divide by what? Our x factorial. And you can see we are getting what? We are getting this value. And I know why we got that is 0.008. Why? Because we had already rounded off here. Okay, let's assume maybe we are taking this value and maybe replacing it here. You can see we're getting what? We're getting this value. Okay, so it was a matter of rounding off. That's why we were getting what? We were getting different values. Okay, so what is this? What is this value which we've gotten? So this is the probability that we will receive 3 calls in the next what? In the next 1 hour. Okay, so this is the probability that we are going to get what? That we are going to receive that is 3 calls in the next 1 hour. And you can see that is the probability is what? It's very low. Okay, you can see the probability is very low. What about if we say we want that is the probability that we are going to receive maybe 10 calls in the next 10 calls in the next, or 9 calls, let's say even 9 calls, okay, in the next 10 that is 1 hour. Okay, so definitely it will what? It will keep varying. Okay, it will keep varying. So that's how we calculate that is the probabilities. Okay, when it comes to what? When it comes to that is our Poisson distribution. Okay, all right. Any question? And also let me just show you an example. As we increase, let's assume maybe the probability that we'll get 10 calls. You will see that the probability will what? Will keep will start that is moving towards what? Towards 1, or it will keep that is becoming big. Okay, yes. So I have that is replaced, that is the factorial, that is our x, and also I will have to replace our x here to 10. Okay, once I replace, you can see it, the probability is now becoming what? It is becoming more compared when we had what? The probability of 3 calls. Okay, Compare this when we had a probability of what? Of 3 calls. You can see the probability was really small. Okay? Yes. Any question up to that point? Are we good up to that point? By show of thumbs up. Are we together up to that point? Any, we are good. Belinda, Michael, we are good. I need, at least I need 10. Yes, okay, yeah, I can see we are all good. That's awesome. That's okay. Good. I want us now to finish, that is with the last slide. Okay, with the last slide. That is the takeaways. Okay, so these are just simple takeaways. That is a Poisson distribution named after that is a Poisson distribution is named after the French mathematician Simeon Denis Poisson. Okay, and it's used to estimate how many times an event is likely to occur within X period of time. Okay, Poisson distribution are used when the variable of interest is a discrete count. Of course, we had seen that. Then many economic and financial data appear as a count variable. Okay, many of economic and statistical data, financial data, sorry, appear as what? Count variable, such as how many times a person becomes unemployed in a given year. That's lending themselves to analysis with what? With Poisson distribution. Okay, and maybe more applications. Okay, yes, that's that's all. That's all for that is Poisson distribution. Unless maybe we have a question, then tomorrow I will be starting on I'll be starting on the practicals. Okay, I'll start with the practicals tomorrow. So I'm going to share a data set before tomorrow's class with you, and then we'll do now the practicals tomorrow. Okay, all right. Otherwise, go and research on exponential distribution. In case maybe you find any challenge, always feel free to reach out to me. Okay, okay, thank you. Any question or any addition? Then in terms of that is in terms of assignments, I've only received the assignment from 3 people. That is Aini, Rosbel, and Dennis Odul. So yeah, those are the only serious guys I have here. Otherwise, I'll review the assignments and then I will get to you individually. Yes. Thank you guys, and otherwise have a great night. If at all you don't have any question. Thank you.